Every 3 is exactly identical to every other number 3. It's almost as though there is an everywhere permeating quality of what it's like to be 3. And if you use this 3 in the US or in old Roman times or anywhere else, it's the same value, right? But the same way that 3 exists, there is a counterpart, a negative 3, and it still has the qualities of 3. There are still 3 things. It's just opposite in sign. When 3 and negative 3 meet, they annihilate, and they make 0. The exact same thing is true about matter. Every single electron that has ever existed has come from an everywhere permeating electron field. And when you dump enough energy into the field, when the field gets excited enough, an electron pops out. But the same way that there's positive 3 and negative 3, there is a negative number for our electron friend. We call it antimatter. And it's exactly the same in every way, except it has the opposite sign. So if the electron has a charge of negative 1.6, then the positron, or the anti-electron, has a charge of positive 1.6 times 10 to the minus 19 coulombs. This is true not just for electrons, but for everything else. Protons and neutrons come from quarks. That's what's inside a proton and a neutron. So the same way that we have this quark field, and every quark that has ever existed has come from the quark field, there is such a thing as an anti-quark. And we write that with a bar across the top, which looks kind of like a negative symbol. It's the negative number. They have the exact same mass, the exact same spin, another quality. The only difference, they have opposite electric charge. In addition to quarks and electrons, the third basic type of matter is something called the neutrino. It's not a neutron. It's not a nucleon. It's something altogether different. You probably have never heard of it, but right now there are trillions passing through your body emitted from the sun. Trillions upon trillions upon trillions. Most of them don't interact with us, and they're really, really hard to detect. But there is such a thing as a regular matter neutrino, and there is such a thing as an antineutrino, which we write, of course, using our bar across the top, kind of the negative number. And just as you can combine 3 with negative 3, and they'll annihilate to make 0, you can combine electron and anti-electron, and when they annihilate, they cancel each other out as well, and in their place they produce energy, specifically a gamma ray photon. So we are going to learn about types of decays that involve electrons and anti-electrons. Because we're fancy, we like to give them another name. In addition to electrons, they are called negative beta particles. Same exact thing, they mean the same exact thing. And in addition to positrons or anti-electrons, we could also call them positive beta particles. That's a synonym. So you can take a moment to copy down these notes. And then let's move on to some of these problems. Consider the equation shown here. Here is a reaction, a decay, and this involves negative beta decay. Now, you can write the negative beta particle the way we've shown here, but it would be perfectly identical and just as valid to write it like this. You have an electron with its negative charge, and here are the values. You might notice that we've put the electron as having no mass. That's because it's so incredibly small compared to the protons and neutrons, the mass rounds to 0. You might also see something funny. For the proton number, we've written -1. There are no protons in this little electron here. There's not a negative proton. The reason we put a negative 1 is because we want this value, the proton number, which is 1 at the beginning, to still be 1 at the end. We want that value to be conserved. Using a negative 1 allows this to happen. The neutrino has no mass, or very, very, very small mass, and no electric charge. Okay, you've got the same thing with the positive beta decay. There is a positron emitted, or a positive beta particle, an anti-electron. And then you've also noticed probably, whenever you emit a negative beta particle, that's regular matter, you also get an antineutrino. And whenever you emit an anti-electron, you also get a regular matter neutrino. There is, it turns out, a similarity here. If you create matter from energy, you have to create antimatter in the same step. Antimatter. If you create antimatter, like this anti-electron, you have to create regular matter in the same step. They are created in pairs out of energy. You can't create two matter particles out of pure energy. You have to create an antimatter and matter pair. Let's try some problems. Number 14 shows a negative beta decay. As soon as you see these are negative beta decay equations, you can write down we've got an electron emitted. So, whoops, hang on. They gave us room for the negative 1 and the 0. And you could write it with an E symbol, you could write it with a beta symbol, but it's the same. Whenever an electron is emitted, that's regular matter. You also have antimatter, which happens to be an antineutrino. And now we can balance. We have 6 protons at the beginning, so this proton number must equate to 6 at the end. So 7 and negative 1, those combine to make 6. If you have 14 nucleons at the beginning, you have to have a total of 14 at the end, so we know that value. This doesn't contribute to either. To do the next one together, this is also negative beta decay, so you've got a negative electron, a negative beta particle, but you could write it with an E instead. As soon as you see you've got matter, there must be antimatter produced as well. And we've memorized also that the values here are 0. 38 is the initial amount. These have to add to 38. 90 was the initial nucleon number. So the mass number, the nucleon number, must be 90 at the end. Those values are conserved. You try these other two. Notice that the products are moving. They have kinetic energy at the end. That means if you add up all of this mass, it would be less than this mass, because some of the mass here was converted into energy. Okay, try those out, and then let's turn to number 15. These are the same type of exercise, but now we're looking at positive beta decays. So as soon as you see it's a positive beta decay, you can write a positive beta particle. You can use the B, the beta, or you can use the electron symbol, either one. And we also know this is regular matter. It's not, oh, pardon me, no, it's antimatter. It's a positive electron. That's antimatter. If you produce antimatter from energy, you have to create matter in the same step. So this must be a regular old neutrino. Then we balance the values before and after. The proton number is 7 here, so it has to add to 7. The nucleon number is 13, so this has to add to 13 as well. You all try the rest of these. The final thing we're going to look at is gamma decay, and the good news is this is the easiest. If we look back to alpha decay, the thing is you start with one parent and it changes to a new identity. Like here, we started with uranium and it changed to an altogether different element. The same is true of beta decay. Look at this. We started with nitrogen and it changed to carbon. That does not happen in gamma. Alpha and beta, the parent will transmute. The parent nucleus transmutes, changes into a different element. In gamma, it stays the same. Here's an example of gamma. All that's happening is carbon changes to carbon. Well, no, it's not even changing. You've got carbon to start, carbon to end, but you emit a gamma ray photon, whose energy, of course, is h times the frequency, h being Planck's constant. So where is that energy coming from? Well, the nucleus starts in an excited state. So it has a little extra energy left over from something else. The parent nucleus will lose energy and therefore lose some mass, which is emitted as a gamma ray photon. So you might see this sort of emission, this type of decay, occurring simultaneously alongside an alpha decay, or maybe you'll see it in a beta decay. So you can have that happen, or it might occur kind of one step after another. So you have an alpha decay that occurs first, and in that decay, you end up with a daughter that has some extra energy. It's left in an excited state. And then that excited state quickly goes away, and we emit a gamma radiation, a gamma ray photon in that second step.